Okay, so we had this beam deflection problem, and it's wanting us to determine the maximum deflection here in region AB of the beam. So AB is going to be between, we have a pin support on the left, and we have roller support on the right. So we want to find what the maximum deflection is in that region. So to approach this problem, the first thing I really want to do here is just kind of sketch out what my deflection is sort of going to look like. So we talked about it in the last video that at the supports, my deflection is going to be 0. So I know that at these two places, my beam is not going to be moving up and down. And I have this load in the middle here. So I can say that this will probably deflect downwards from that load and then come back up to 0 at this support. And then I have a distributed load and then a concentrated load at the end of the beam. So it's going to come back down something like this. Right, so there's going to be a distance y over here, and there's going to be a distance y over here. And we want this one is what we're looking for because it asks for region AB in the beam. So that's kind of the first thing I do. And when we do that, we can kind of see what our boundary conditions are going to look like. Basically, it's going to be that at A, so at x equals 0, right, and at B, which is going to be x equals 12 feet, we're going to have a displacement of 0. So let's just write that down. So we know that before we even do any math here, our boundary condition. So for this beam, I'm going to have at x equals 0, right? So at A, my displacement, or my deflection, excuse me, so that's going to be y, is going to be equal to 0. And I also know at the other support, so at x equals 12 feet, my y is also going to be equal to 0. There aren't any boundary conditions I can use right away to figure out that have to do with the slope, because at these supports, my slope is going to be non-zero, right? Because both the pin and the roller, the beam can rotate there. But if we had a cantilevered beam, which we don't, then we could say the slope is also going to be equal to 0 at the cantilever support. But we will be later, we're going to be using slope to figure out this maximum over here. So what we're going to be using for this is be using something called the discontinuity functions. So I kind of put out a little chart over here. Basically what happens is we make these angle brackets, and if my A value, which is going to be where I am with a certain load on the beam, if that is going to be less than x, so where I'm looking at, it's going to be 0. And so it's only defined if this thing in the angle brackets is positive. So it'll make more sense once we get into the example. But basically our first step is that what we're going to do is to solve this problem, we want to write an equation for moment. So I made this chart on the right here that lists, it's kind of like a cheat sheet. So it kind of lists out what the different, if we have different types of loads, what those are going to be. So if we have just a couple moment somewhere, right, we can just write that a moment is basically, it's just equal to the couple moment, right, times x minus 8 is 0 power. So that's just going to go to 1. So basically our moment is equal to our moment. That kind of makes sense. If we have a concentrated load, right, it's going to be equal to the magnitude of the concentrated load, and then x minus a to the first power. So moment force, this kind of is analogous to force times distance. And then we have these two things with distributed loads here. So for a rectangular distributed load like this one here, right, it's going to be w over 2 times x minus a to the second power. Remember what w is? W is going to be the magnitude of the distributed load. So, or not the magnitude of, it's just whatever if it's 2 kips per feet, that W is 2. So in this case, it's 2 kips per foot. So it's going to be 2 over 2. So that's going to be 1. If we had a triangular distributed load here, which we don't, it's going to be, this isn't W, this is M. So it's going to be the slope. This is the slope here. So it's the slope of the triangle over 6 and then x minus a to the third. And the nice thing about discontinuity functions is that we only have to write one equation for the whole beam. So if we were doing this using, there's also another way called a method of integration. We'd have to split up the beam into sections and write a different equation for each section. But with the discontinuity function, we only have to write one equation. But the kind of weird thing about this whole thing is that if we have distributed loads, so if we have either the rectangular distributed load or the triangular distributed load, when we write our moment equation, it's going to assume that these loads go all the way to the end of the beam. So one thing we have to check on our model up here is if do all our distributed loads go to the end of the beam. So they actually do. In this case, we have one distributed load, 2 kip/feet. It starts at x equals 12 and it goes all the way to the end. If we had something where there was a beam and the moment, let's say we had a rectangular distributed load and it stopped, right? So let me make a quick example here. Let's say we had a beam, right? And we had a distributed load like this, right? And maybe a pin and roller. What we have to do, and we'll do an example of this at some point, is we basically have to extend this distributed load to the end and then put another one going up the equal and opposite to cancel that out. But in this case, we don't have to do that. So don't worry about this right now because it's not super important for this problem. So let's just go back to looking at this problem. So what I'm going to do now is write an equation for the moment for the entire beam. So I gave you the support reactions here. So AY is actually going down, which is kind of weird, 1.5 kips. BY is going up 22.5 kips. So let's write an equation for the moment using these relationships over here. So the moment here for the beam, I'm going to work my way left to right. So another way we can write this is the moment is equal to EI. So the modulus of elasticity times the moment of inertia. And that's going to be the second derivative of displacement with respect to x. Because remember, if we integrate moment twice, we get the displacement equation. And so we're going to rewrite this as, okay, so I have AY going down 1.5 kips. So let's go to my chart. So I know M is going to be the magnitude of the load times x minus A to the first power. A is going to be wherever that load is taking place. So in this case, the AY is taking place at A equals 0 because it's going right at x equals 0 here. So I'm going to write negative 1.5 because AY is going down. And it's going to be x minus 0 to the first power, right? Because moment for the concentrated load is x minus A to the first power. Okay, so that's taken care of. Next, I have a 6 kip concentrated load over at x equals 6 feet. So I'm going to do the same thing, but this time my magnitude is going to be 6 kips, right? And instead of x minus 0, what is that going to be? Well, now it's at 6 feet, so it's going to be x minus 6. And that's still going to be the first power, right? And we have another concentrated load. So we're done with this 6. So now we go to this by here. That's going up, so we're going to write plus. So that's going to be plus. The magnitude of that is 22.5. And that's going to be at x equals 12. So x minus 12 to the first power, right? We still have a couple more things we need to take care of. We have this 2 kip per foot distributed load here. So what I need to do with that is use this part of it. So the W over 2 x minus A to the second power. But our W is going to be 2. So it's just going to be 2 over 2, but it's going down. So we're going to put minus 2 over 2, which is just 1. It's going to be x minus 12 because we use wherever the point is that the distributed load is starting. So since it's starting at x equals 12, we just put x minus 12. We don't do like where the center of it is. No, we just do where it starts. So it's x minus 12. Since it's a distributed load, we do x minus 12 to the second power. And then we have this one thing at the end, this 3 kip concentrated load. So let's just write that for now. So we're going to write minus 3, that's the constant, that's the magnitude of it, and it's going to be x minus 12 plus 6 is going to be 18, and that's going to be the first power. So that's going to be our moment equation. Now the interesting thing about this is when we plug in numbers, right? So if we plug in an x value, so let's say we want to find what the moment is at x equals 6, right? We could plug in x equals 6. Right? So anything where the inside the bracket is defined, anything where the inside the bracket is positive is defined, anything where it's negative is undefined. So if we plug in 6, this would be okay, right? This would be fine because it's 6 minus 6. So it's going to be 0, but it's still defined. And all these 12s and everything and 18 is all going to go to 0. But the thing is, we'll never have anything where we're greater than x equals 18, right? Because the whole beam is only 18 long, and if it's x 18 minus 18, that's just going to be 0 anyway. So we can actually just forget about this whole term right here when we're doing the integration, this last term here. So if we have a concentrated load at the end, we can just forget about it. Now, that still means it's affecting our equation because it's still part of the support reactions that we calculated. But when we integrate it, the nice thing is we don't have to worry about it. So the next thing we need to do is to find the slope equation. So we know that the slope is going to be equal to EI times the first derivative of displacement. So that we're just integrating this. We're just doing an integration, and we're going to get slope. So we integrate this whole thing up here. So when we do that, right, we're going to have, so it's going to be, this is going to be raised to the second power, and then it's going to be negative 1.5 divided by 2. So that's going to be negative 0.75. Now we just keep the angle brackets. So it's going to be x minus 0 to the second power, right? This thing, we're going to integrate this. We're going to get minus 3 x minus 6 to the second power. 22.5 divided by 2 is going to be 11.25. So it's going to be plus 11.25 x minus 12 to the second power. Now we need to integrate this guy. So that distributed load. So 1, right? This is actually going to be 1. But then we're raising it to the third power. So it's going to be minus 1/3, right? X minus 12 to the third power. Right, and this part's 0, so when we integrate 0, we're going to get a constant, right? So don't worry about this, actually, it just goes away. But when we integrate everything, remember, we're going to have a constant, so we need to add a plus C1 here. So it's some unknown constant that we're going to have to solve for. So this is our slope equation, so we need to integrate this one more time to get the deflection equation. So let's do that, right? So we want to find deflection, we want to find an equation for deflection. And that's just going to be EI times Y. Y is going to be our deflection. So we integrate dy dx, right? We're going to get Y. So let's just do this last part out, right? So we have second power here. So we're going to go up to the third power. So negative 0.75 divided by 3 is going to be negative 0.25. X minus 0 to the third power, right? And let's just finish this off. And then we integrate this again. So that's going to be minus 1, x minus 6 to the third power. And then this is going to be plus, this is going to be 11.25 divided by 3. So that's going to be 3.75. And that's going to be x minus 12 to the third power. Right, and then we have to integrate this guy. So negative 1/3 divided by 4 when we integrate this is going to be negative 1/12, I think. Yeah, negative 1/12 x minus 12 to the fourth power, right? And we're going to need to integrate this constant. So it's going to be plus C1x. Then we're going to have another constant because we're integrating this again. So it's going to be plus C1x plus a C2. So this is going to be our deflection equation here. So this is kind of what we're looking for at the end, right? Deflection equation, and here is going to be our slope equation, right? So these are kind of our two really important equations that we need to use. So let's kind of go back, and we still need to figure out what these constants are going to be. So let's go back and look at our boundary conditions, and we're going to use our boundary conditions to figure out what our constants are going to be. So when we look at our boundary conditions, right, we see that at x equals 0, y equals 0, and at x equals 12, y equals 12. So we're going to plug these boundary conditions into our equations. So these boundary conditions, these both have to do with y. They both have to do with deflection. So we're going to use our deflection equation. So whenever I see an x equals 0, y equals 0, that's usually a good start because a lot of stuff goes away when I do that. So let's use our first boundary condition, right? So now we need to solve for a constant. So let's do at x equals 0, y equals 0. So I'm going to plug in y equals 0 to this equation. So that becomes 0, right? Then x equals 0. So remember, if it's 0, anything is 0, right? So 0 minus 0 is 0. So that's just going to go away to 0. So anything where x is less than a, so x is always going to be less than a in this case because we have x minus 6, x minus 12, x minus 12, x, all this x minus 12 stuff. So all this stuff here, all this stuff is going to go to 0, right? 0, 0, 0. So and this goes to 0 too. So I'm basically left with 0 is equal to, this is all going away to 0. So I'm left with 0 is equal to C1x plus C2. And also this x is 0 too. So x is going away. This is also going to 0. So I'm just left with 0 is equal to C2. So I just found C2. So we just found C2. So let's just write this over here. Oh, and we don't want MATLAB to open. Sorry about that. So we're going to get C2 is equal to 0, right? So next thing we want to do is we want to plug in and let's just get rid of these, some of these here. We want to plug in our second boundary equation. So our second boundary equation, we go back up, is that at x equals 12, y equals 0. So let's go down here and write that out. So at x equals 12, y equals 0, right? So we're going to be plugging in x equals 12 to this equation to figure out our second constant, and y equals 0. So if we take this equation down here, right, we're going to have that since y equals 0, right? So we're going to have 0 on the left side is equal to negative 0.25, and we're going to have x minus 0 to the third, but since x is going to be 12, we're just going to have 12 to the third power, right? And then we're going to have minus 1, and then that's going to be 12 minus 6 to the third power, plus C1x, so x is 12, right? And then we know C2 is 0, so we don't have to even include that, right? And we need to find the C1 constant. So if we do that, we move everything over, right? So we're going to get, basically simplify this out, you're going to get negative 432 minus 216 plus 12 C1 equals 0. So we're going to end up getting that C1 is equal to 54. Right? We're going to end up that C1 is equal to 54. So we can write that up here. So C1 is equal to 54. So these are our two constants. And now that we have these two constants, we know we can kind of rewrite our equations to see what those are all going to be, right? So up here, instead of C1, right, we can just plus that's going to be 54. So this is going to be 54x, right? And then C2 just becomes 0, right? So let's just go back to our problem and see what they're asking. They're asking for determine the maximum deflection in region AB. So we kind of talked about this before. Our maximum deflection in AB is going to be where our slope, at the x value where our slope is equal to 0 for this. So the first thing we need to do is calculate that x value where slope equals 0. So the good thing is that we have our slope equation, right? So we can use that slope equation to find the that x value, and basically you're going to be solving for x. So let's just copy and paste. This is going to be our slope equation, and we need to find where the slope is equal to 0. So let's do that. So we want to find where slope is equal to 0. So we're going to say our left-hand side is going to be equal to 0. And we're basically just going to replace all these x minus 0 stuff with just normal brackets. But we're not going to include anything that, since we're only looking in region AB, we're only going to include up to 12 feet here. So we can just rewrite this equation as 0 is going to be equal to negative 0.75 x squared, right, minus 3 x minus 6 to the second power, right? And then we're going to have plus 11 point, actually no, just plus, since this is x minus 12, we're just going to have plus 54, right? And we're going to be solving for x. So what you need to do is actually distribute this x minus 6. So you just need to do x minus 6 and then x minus 6 and distribute that. You end up getting x squared minus 12x plus 36. I don't know why my pen isn't really working that well. You get plus 36. And then we're going to solve for x. So we can kind of rearrange this. When you simplify everything, you're going to get 0 is equal to 3.75 x squared minus 36x plus 54. And so you'll end up with an x value of approximately 7.739, right? But since this is quadratic function, you're also getting another x value. X equals 1.86. And these are both going to be feet. That's supposed to be a foot. These are both going to be feet, but only one of these probably makes sense. So let's go back up here, right? X equals 1 would be here. Somewhere here. Do you really think that the slope is going to be 0 here? It's probably going to be closer to that 7.73. So it's probably going to be somewhere around here. So I'm just going to forget about that 1 value, right? So that's definitely not it. So I'm going to use this x equals 7.739 feet. So that's what I'm going to use. So what I need to do now is plug that into the deflection equation. So I plug that x value into the deflection equation. Okay, so this is what my deflection equation ended up being. So now I need to plug in the 7.739 into this, but I can forget about anything where the 7.739 is less than a. So this is going to go away, and these two, this is going to go away as well. So I just only need to plug in the rest of the x's. So I'm going to move this EI over. So I'm going to have y, which is going to be my deflection, is going to be equal to 1 over e times I, right? And I'm going to plug in x. So it's going to be 1 over EI, right, times negative 0.25, 7.739 to the third, minus 1, 7.739 minus 6 to the third, right? And then plus 54 times x, which is 7.739. And if I do that, I'm going to get y. If I plug everything in, get y is equal to 296.77. The units on here are going to be kip times feet to the third, and that's going to be over e times I. So you might be wondering, where did these units come from? Kip times foot to the third. So let's go back to our equation so we can kind of see where that comes from. So moment, right, that's going to be, since our forces are in kips, right, and our distance in pounds, we know moment is going to be a kip foot, right? Because that's just what a moment is, pounds times force. We're integrating with respect to x. X is a distance in feet, right? So if I integrate, I'm going to get kip foot to the second, and then I integrate that again, I get kip foot to the third. So that's where the kip times foot to the third comes from. So now that I have this, when I divide by e and I, my e is in kips per inch squared, right? KSI. And that's going to be 29 times 10 to the third, I believe it was. That's going to be KSI. So I have inches over here, and my I is going to be in inches to the fourth. So that's going to be equal to 204 inches to the fourth. So I have a foot, and then now I have inches over here. So I need to convert this kip foot to the third into inches to the third. So the way I need to do that is going to be by multiplying, since I have a foot to the third, and there's 12 inches per foot, I need to multiply by 12 to the third. And when I calculate when the actual deflection is, I'm going to do y. So now I'm calculating for my deflection. So when I calculate when my actual deflection is, right, I'm now going to do y is equal to, so it's going to be 296.77, and that's going to be kip foot to the third. I need to convert that to inches, so I'm going to multiply by 12 inches per foot and that's going to be the third power, right? And then I need to divide by EI. So I have these over here. So it's going to be divided by 29 times 10 to the third. That's going to be kips per inches squared. And then also multiply by 204 inches to the fourth. So when I do this, I should just be left with a unit of inches, right? So on the top, I have kip inches to the third. On the bottom, I have kip over inch squared and then an inch to the fourth, right? So this inch squared is going to cancel with this 4 and become a 2. So I have these two kips will cancel. So I'm going to be left with an inch to the third over inches squared. So yeah, that's going to be just an inch. And when I do that, I'm going to have my total deflection. So my maximum deflection in the middle, that region AB, is going to be 0.0867 inches. And that's going to be my answer that I'm left with. So this is kind of a lot. There's a lot of steps that we have to do in this. And obviously, it's a little complicated. So hopefully you'll understand how to do this a little better. And hope I helped.